Okay, this is a video over the notes on inductive and deductive reasoning. It is a second lesson from the geometric figures unit, and these notes were given on Friday, and then they'll be given on Monday to B-Day. So if you missed class, please print out the blank notes and follow along. So we're going to be talking about two specific kinds of reasoning today, and those are inductive and deductive reasoning. Inductive reasoning is the art of looking at given information and identifying patterns. Deductive reasoning is the art of applying definitions and rules or laws in order to draw conclusions. So let's get those definitions in here first and then start working through the examples. So what is inductive reasoning? The examination of data in search of patterns. So inductive reasoning, we look for patterns. And then what do we do with those patterns? We make a conjecture about what's going to happen in the future if the pattern that we think we see is accurate. So what is a conjecture? Is essentially an educated guess based on inductive reasoning. That says guess based on inductive reasoning. And then let's just do some inductive reasoning real quick. A4, C8, E12. Looks like we're alternating every other letter. So A, B, C, D, E, F, G, H, I. 4, 8, 12, we're counting by 4, 16, 20. I'm sure this is something you could have done on your own. 2, 4, 8, 16. It looks like we're doubling every time, so 32, 64, 128, 256. 3, 8, 13, 18, 23. So it looks like we're adding 5 each time. And I think that 8, 3, 8, 3 pattern is going to continue. So 28, 33, 38, 43 if we just keep adding 5. And then here, this one is a little bit more difficult to discern. But we're here, first we add 1, then we add 2, then we add 3, 11 minus 7 is 4, so we're adding 4. So the next step would be to add 5 for 16, then add 6 for 22, add 7 for 29, and then add 8 for 37. So inductive reasoning. We look at information and we establish a pattern. And this is a great example in mathematics where we use inductive reasoning. And then we make these guesses about how the pattern continues. That is the conjecture. Now, unfortunately, inductive reasoning has limits. So we're going to look at examples 5 and 6 and see how we could take limited information and draw two completely reasonable conclusions based on that information. So it could be that example 5 is like example 2. 2, 4, 8, 16, and then it just keeps doubling, 32, 64, etc. But it also could be that example 6 is somewhat like example 4. We could go plus 2, and then plus 4, and then the next thing would be plus 6 for 14, and then plus 8 for 22, and then plus 10 for 32. So those are two patterns, two conclusions, different conjectures that can be made based on the same information. So because of inductive reasoning has its limits, we want to develop a stronger type of reasoning called deductive reasoning, and that is reasoning based on definitions and rules. And generally these definitions, or these rules, are the rules of logic. Specifically in geometry we use postulates and theorems that we've already proven, and of course definitions. So let's look at some deductive reasoning, but before we do that we need to get some basic geometry definitions. What is a postulate? That is a statement so simple and obvious that it does not require proof. And that does not is important. Postulates do not require proof. Theorem, on the other hand, does, and we'll get to that in just a minute. First, what is a formal definition? We practiced doing formal definitions during the last class, or the last set of notes. In geometry, our formal definitions are all built on the undefined terms. So a formal definition is an agreed upon meaning. Or description of a mathematical idea. Let's say idea or object. And of course we have definitions that are not inside of math, but we're going to stick with the notion of definition in geometry. Okay, and then a theorem is a statement that does require proof. So there's a compare and contrast of postulate and theorem that's pretty important. Postulates do not require proof because they're so obvious. Theorems are a little bit less obvious, or maybe they're not, but theorems they do need to be proven. They're not something we can take at face value. We actually have to prove that theorems are true. Okay, so let's look at an example of a proof and a two-column proof, how we're going to do those. So we're going to prove that line AB contains line segment AB. And I'm going to give you a postulate while we do this. First, we've got to put a couple points on that line. And just by looking at it, it's obvious line segment AB is in fact on line AB. But to prove it, we have to go through a formal reasoning process. And proofs almost always start with our given information. So we say line AB is given. And I've kind of combined it here. Line AB, reason, it's our given. It's right there in the picture. That's what we're starting with. Now the next line of our proof, line AB, contains points A and B. And that right there is our linear postulate. So this is something we can take on faith. The reason we say that line AB contains points AB is because we know all lines are connecting 2 points and going on indefinitely by definition or by formal description. So we just take that sort of that undefined term, that common understanding of a line, and we turn it into the linear postulate. All lines connect to 2 points and go on forever. So we consider that obvious enough to not require any proof. And then to finally conclude that line segment AB is in fact on line AB, we're just going to use the definition of a line segment from the last set of notes. Line segment AB is on line AB by the definition of a line segment. So this statement, reason, based on that first line, I can conclude this statement for this reason, and based on that I can conclude this statement for this reason. This is the process of deduction or deductive reasoning, and it's the backbone of the proofs that we write in geometry. And let's always remember that we're going to be comparing that type of reasoning to this type of reasoning here, inductive reasoning, where we're just looking at some information and saying, oh, okay, I think I see a pattern, and then making a conjecture or a guess about how that pattern is going to continue. And for our proofs, maybe we can treat this like an outline, and we can summarize in a sentence or two. So maybe we'll say line segment AB is on line AB by definition. Okay, now we're going to do some more proofs here. Super simple. We're going to do like an arithmetic proof, basically. So I know that you can do this math, but we're going to take that math and do it in proof form. So what would you want to do first to solve this? You can really pick anything. I'm going to start with the addition. But before I get to the addition even, generally speaking, you are always going to start your proofs with the given statement. So this information is given to us, so this is what I'm going to base my conclusions on. I know I can add this stuff together. So 1 and 10 and 3 is 14 minus 2 equals 3 times 4. How do I know that? Because of the law or the rule of addition. And then 14 minus 2 is 12. So 12 equals 3 times 4. I'll separate these out a little bit here. How do I get from this step to this step? Subtraction. And then I know that 3 times 4 equals 12 by multiplication. And that's it. I've proved that those two sides of that equation are equal to each other. And so the summary here, I can just sort of go to the given. 1 plus 10 plus 3 minus 2 equals 3 times 4 by the rules of arithmetic. Alright, so now we're going to sort of up the ante here and do an algebra proof. Given this information, we want to prove x equals 10. We're always going to start with the given, or 95% of the time we start with the given. There are some proofs where you might end up using the given elsewhere in the proof, but usually it's at the beginning. So that is given to us. Now, one thing I'm not going to allow for is substitution. We can't just plug in x equals 10 and say, okay, there we go, I got it. We're going to have to do a little bit more formal than that. The first thing I would do in solving this would be distribution. So that would be 3x minus 6 equals 2x plus 4, and then I just write the reason. And the formal name for distribution is the distributive property. Okay. And now we're going to take these basic rules of arithmetic and use the algebra versions of them. How about I subtract 2x from both sides, and I'm going to try and do that without showing my work. And I'm just going to write out the next line of the proof. If I subtracted 2x from both sides, I would end up with x minus 6 equals 4. And that is the subtraction property of equality. And I don't just get to say subtraction, I have to say property of equality because I subtracted something from both sides of the equation, as compared to over here where I just subtracted something on one side of the equation. Again, this time we'll use the addition property of equality by adding 6 to both sides to get x equals 10. That is the addition property of equality. And then we've done it. We've accomplished our goal. We've proved that x equals 10. Alright, and so our summary would be something like x equals 10 for 3x minus 2 equals 2x plus 4 by the rules or laws of algebra. Or maybe we would even call these properties. By the properties of algebra, we know that x equals 10 for this expression, for this equation. Okay. And there's 2 more examples here in the notes. Should be example or proof number 5 right here. I guess I'll go ahead and work through those quickly. Prove that line AB contains ray AB. Well, we add in the points AB, and we'll say line AB is given. Line AB contains the points A and B by the linear postulate. And just like last time, we're going to conclude with the definition. The definition of array is to begin from one point and go off in the direction of another point indefinitely. So, line AB contains ray AB. Definition of array is how we know that's true. And I'll leave the summary up to you. Maybe you can treat this like an outline and write a summary of what was done here. And then for this one here, we're going to start with our given, and we're going to do algebra to prove that x equals 90. And I'm going to get you started. This one is actually sort of interesting. You might be tempted to do distribution first. But if you notice, 4 is divisible by 2. And 4 and x plus 5 are multiplied together. So that means we can simplify to 2 times x plus 5 equals x plus 100. And that was division. Not the division property of equality, because all I did was divide on one side of the equation, so it was just division. And then at this point, I think you could finish the proof. I'll go ahead and do it, just trying to not make this video too long. We just use the distributive property, so the reason is the distributive property. And then if we subtracted x from both sides, we'd have x plus 10 equals 100. That is the subtraction property of equality. And if we subtract 10 from both sides, we get x equals 90, again using the subtraction property of equality. And at this point we have proved what we set out to prove. So you could write a short summary here of this expression has x equals 90 as a solution, or this equation has x equals 90 as a solution because of the rules of arithmetic and the properties of algebra. And then the homework assignment, I know it just says practice, but this is in fact homework. And it's got some examples of inductive and deductive reasoning here, and a couple of algebra proofs on the back, and then a couple of algebra equations that you just have to solve. So there you are. I hope that video was helpful.